Welcome to Module 6, Reliability Engineering for BAS Managers. In this module, we move from fixing failures to designing a program that reduces failure, detects degradation early, and recovers safely when something still goes wrong. Reliability is not luck. It is a professional discipline that combines architecture, maintenance, spares, backups, alarms, testing, documentation, and trained people. By the end of this lesson, learners should be able to explain reliability terms, identify weak points in BAS infrastructure, define recovery objectives, and connect maintenance, spares, alarms, data, and training into one operational reliability program. A building may contain expensive equipment and still be unreliable. Reliability depends on design, installation, maintenance, operating practice, documentation, spare parts, recovery capability, and people. The practical question for a BAS manager is whether the building can continue to perform its required function and recover safely when something fails. Reliability, availability, maintainability, resilience, and redundancy are related but different. A system can rarely fail and still have low availability if restoration takes too long. A redundant system can be fragile if both sides share the same power, network, software defect, or maintenance error. MTBF measures the average time between failures. MTTR measures the average time to repair or restore. A simplified availability formula is MTBF divided by MTBF plus MTTR. This formula is useful for comparison, but it is not a substitute for defining the required function and verifying the quality of the incident data. A single point of failure is not always one device. It is any dependency whose loss prevents the required function. Two servers connected to the same failed storage array may still represent one functional point of failure. Reliability review must look for hidden shared dependencies. False redundancy occurs when the backup exists on paper but cannot take over the required function. It may be disabled, share a failed power source, contain outdated software, have insufficient capacity, or require an operator action nobody practiced. Redundancy must be proven by a functional test. Criticality should be based on consequence, not equipment size or replacement cost alone. A small sensor or valve can be critical if it protects a high-value process, safety condition, or regulated environment. Criticality should drive alarms, maintenance, spares, redundancy, testing, access, and lifecycle investment. Recovery objectives should be defined before an emergency. The manager needs to know what function must continue, how long the organization can tolerate loss, how quickly service should be restored, how much configuration or data loss is acceptable, what degraded mode is permitted, who has authority, and what resources are required. Reliability is strengthened through independent layers: sound mechanical and electrical design, local control and safe failure modes, redundancy where justified, preventive and predictive maintenance, meaningful alarms and trends, verified backups, tested recovery procedures, critical spare parts, trained backup personnel, and incident learning. Reliability-centered maintenance starts with function. What is required? How can it fail? What is the consequence? Which maintenance strategy is technically and economically appropriate? Examples include testing controller backups, exercising standby pumps, inspecting UPS batteries, verifying actuator stroke, reviewing network errors, and restoring a server image in a controlled test. Spare parts should be selected by consequence and lead time. A controller on a shelf may not be a usable spare if the programming tool, license, database, correct firmware, or trained person is unavailable. The manager should evaluate spares as complete recovery capability. This field example shows the difference between installed redundancy and demonstrated redundancy. The standby pump started, but it did not deliver the required flow because a valve was left partially closed. The corrective action was to test the outcome using differential pressure and flow, not only the motor start command. Server and data reliability includes the application, operating system, database, historian, backup retention, protected copies, recovery sequence, credentials, certificates, vendor support, and network dependencies. A snapshot may support rollback, but it is not automatically a complete backup strategy. A backup is only proven when it has been restored. The common mistakes are practical: Counting installed devices instead of testing functional redundancy, maintaining everything the same way, ignoring recovery time, keeping backups that have never been restored, neglecting credential and knowledge single points of failure, measuring uptime without defining function, and closing incidents after restart without correcting cause. The exercise asks the learner to select one critical service and map the physical equipment, controllers, power, network, server, software, access, documentation, and people required for that function. Then they identify common dependencies and define preventive, detective, and recovery controls. Use this knowledge check to reinforce the difference between installed redundancy and proven redundancy. The correct answer is B. The system has shared dependencies and untested recovery. Another dashboard does not improve recovery capability. Disabling alarms increases risk. Waiting does not address current exposure. In this module, learners saw that reliability is not accidental. It is engineered through architecture, maintained through purposeful tasks, measured with context, tested through recovery exercises, and improved through learning. Next, Module 7 takes these reliability concerns and turns them into a structured risk management process.